So hi everyone. Today I am going to have, I will demonstrate the UK example for excess market return predictability, and we will go through the each part of the MATLAB codes and discuss that how the data are processed, and we will run the forecasting routines together as well. And finally, I'm going to provide some tips how to customize the scripts for your own analysis, right? Okay, and so basically, I'm going to have my notes with me as well, so that I make sure that I'm going in the right direction. So let's us start. Okay, so as in the slides, you know that clear means that it's going to remove anything in the workspace, and CLC means it's going to remove anything in the command window. For example, I am just doing this, copy and paste, right? So we have here the data in the workspace, and we have the codes in the command window. But if I do the clear and okay, let's do it one by one. So it's going to remove everything from the workspace, and CLC, it will remove everything from the command window. Now, one thing I want to mention here, that if I just like Control C and Control V here, it's going to take me a lot of time to do this. What I will do is that we have here run section, right? So if I click here, and we have this is somewhere in between these two blue lines, right? So anything starting with double percentage, meaning that a new section is started, right? So with if I remove this, so it's going to be the same section. So if I double this, then it's going to be a separate section. Now I will select, instead of copy pasting this one, I will click in this section and I will go for the run section, right? Oh, okay, let's run this one. Now I will click here in this section and run section. So now this will give us the results, right? So rather than copy pasting it, I think that I will get confused with this. So I will do this run section. Okay, right. So first of all, loading data from 1993 December to 2019 December, and this is our in sample period is 1993 till 2006, right? And our hypothetical out of sample period is 2007 January till 2019 December, right? So first of all, we are going to read the CSV comma separated values file, right? And we'll exclude the first column and first row. Okay, so we only have the data rather than having the names of the independent variables and having the date column, right? And then we have the we are going to define the stock variable, right? From this, the first column will be our the UK total return index. Then we have dividend yield, and that is the second column from the data is going to be the UK dividend yield. And then we have risk-free rate, right? So this is not the total return index. Basically, we are using UK T-bill rate for calculating the risk-free return and excess market returns, right? So that is in the third column. Okay, so let me run this section, and then I'm gonna show you that we have this data here, right? And why it's not loading, right? So here we have 3 1/5 double, right? Okay, so first one is the UK return UK total return index, right? And second one is the dividend yield. Third one is the risk-free rate. And then fourth one would be the short-term yield, and fifth one would be the long-term yield, because we need these for calculating the term spread for the UK, right? So I'm going to close this now. And then we have to compute the UK variables, right? Now we have to calculate the market return, so stock to end, and this is element by element divisions, right? And stock 1 to n, right? So this is going to be like starting from 1994 Jan 1, and sorry, not Jan 1, January 1994, and this is going to be until the 2009 December, right? And then from here, the one value with 1 to n minus 1, this is going to start from 1993 December and going to end until 2019 November, right? So this is market return. And then we have the risk-free rate. Okay, so starting from 1 till n2 minus 1. And now this is important here, divided by 1200, meaning that 12, we're dividing it by 12, we don't need the annualized RF, right? And then with 100, we don't need it even in the percentage form, right? So risk-free return, neither annualized nor percentage, right? So that's why divided by 1200. And then we have the excess return calculations from 1994 to 2019, 2019, yeah, and this is going to be 312 observations. So we will have this Rx, excess market return vector, which is 312 by 1, right? Dimension. Then we calculate the term spread, right? So 2 to enter to 5. So 5 means this is the long-term yield, and the number 4 column indicates the short-term yield. So difference between them and then divided by 100. We will get the term spread, right? And finally, we will have the log of dividend yield, and we will save this as dy. Okay, so here we have Rx, excess market return, as our dependent variable, UK, and then we have UK term spread as our independent variable predictor, and we have dividend yield of the UK as another second predictor, right? And let's just run this section. So I'm going to show you the dimensions of this. Like, for example, here we have RM 3112 by 1, right? We have RX 3112 by 1, 312 observations, right? 156 in sample plus 156 out of sample observations, right? And then we have dividend yield 312 by 1, right? Okay, so that was the UK part. Now we have to load the Goyle and Welch data. So basically, we are using the 14 US predictors from the Goyle and Welch data right into our regressions. And for that, we need to load this program generate DW predictor 2.mat, and it includes the 14 US variables. So these are all the 14 US variables, but here you have to be careful because this data is available from 1973 till 2022, okay? But we need the data from 1993 to 2019, right? So we're gonna use the data starting from 253 until 564, okay? So column 1 will be the log dividend price ratio, then we have dividend yield, earning price ratio, etc., right? So please make sure that your data is consistent across all the predictors, right? Okay. So did I run this section? No, I didn't. So let's just run this section. Okay. So now we have our 14 US predictors as well. Okay. Compute market excess return forecast. Now we have to do the out of sample forecasting, and our out of sample period is starting from January 2007 until the December 2019. So meaning that we have 156 observations right here. So our Y variable is our dependent variable, okay, the target variable. We define this as the excess return that we have calculated here, right, this one. And then we have our T of length Y. So total number of observations, this is going to be 156. And then our outer, no, sorry, not 156. T is the total number of observations. This is going to be 312. So M1 is out of sample, sorry, in sample period, right? And these are 156 observations. And then we have M2 out of sample, hypothetical out of sample period. Our observations are 156, right? Okay. Let me just run these three so that I can show you the dimensions. T1 Y, T, M1, M2. So what? M1, 156, M2, 156, right? And we have Y, total number of observations, 312, right? And that is T, actually. And yeah, that's right. Now, we have to define all the 14 US predictor variables plus the 2 UK predictors, the term spread and dividend yield, into a one big set. And that is, we are going to define it as X. So in X, we are going to put all the 16 variables together. So the first two are the UK predictors and the last 14 are the US predictors, right? And then what is J here? J means the number of predictors. So the size of X2, meaning that the, okay, let me run this X. So where is X? So 312 by 16, right? So it's a double, and meaning that size of X2, meaning that we're going to have 16 predictors. So J size X2 will give you J equal to 16. So we have number of predictors equal to 16, right? Then in order to save the results from our out of sample forecasting, we need to basically we have to define some vectors and matrices to save our results, right? Based on different forecasting techniques. For example, if we are forecasting based on prevailing mean, then we're going to save this as not a number as M2 and by 1, right? And if we are forecasting based on predictive regression with expanding window, right? So this is going to be by M2 by J. So it's meaning that's 16, right? 156 by 16 dimensions. Similarly, we will do all the results we're going to save based on the predictive regression with rolling window. Then we are combining, expanding, and rolling for each J. We're going to save this in forecast window combine. And then we will do the combine the expanding across J, rolling across J, combine of expanding and rolling across J, and save in forecast combine, right? And then we will do the diffusion index, the PCA, principal component analysis, also based on expanding and rolling windows. So forecast TI expand based on expanding window, forecast TI roll based on rolling window, and then combination of both for expanding and rolling, right? Okay. So up till now, we have just defined all the variables, right? And just created the vectors and matrices to save the results. Now, we have to start from the for loop where we will iterate over the out of sample period. So what is our M2? M2 is basically 1 till, small m2 is basically 1 till capital M2, right? So our capital M2 is, the 156 observations, right? So for each observation, we are going to iterate, right? So from 1 till 156. So we define the variable ym2 based on the expansion window. So if m2 is equal to 1 here, so 1 cancel, we're going to have the in-sample period here. And if m2 is equal to 2, then 2 minus 1, 1. So this is going to be the first observation for the outsample period, right? Then we have also same for our dependent variable xm2 expand, right? We have, this is based on expansion. Now we have both an independent and our predictors based on the rolling windows, okay? And we have our benchmark model prevailing mean forecast, right? So which is, again, the same, we have to define that y1 to m1 and m2 as we go from 1 to 156, right? Now, we have another loop, for loop within a for loop, because we know that our predictors, our number of predictors is equal to 16. So j is equal to 1 to j, right? And for that, we need to, estimate the ARDL. Okay, you all are aware of what is ARDL, autoregressive distributed lag model, right? So here, our dependent variable is ym2 expand, right? Our independent variable is xm2 expand for j number of predictors, right? We have 16 variables here. Here, 1 mean horizon forecast is 1 month, and 0 means that we have 0 lags for the dependent variable, right? And 1 means we have 1 lag for the other variables, the predictor variables, the one in X, right? Okay, so once we get the gamma hat M2 expand J from by estimating this ARDL, we would get the coefficients, two coefficients from this, and then we're gonna multiply the we're gonna multiply this with the X M2 expand, and we will save the results in forecast expand PR M2 J. Right, so meaning that J for each predictor, we're going to save the results. So basically, this is for expand, right? So same will be done for the rolling, okay? And then same will be done for the forecast window combine, right? Okay, so once we are done with all the predictors, next thing, okay, so one thing here, I want to mention very clearly, Professor Sunchen definitely has mentioned in his email that you have to take care of the multicollinearity. Okay, if you are using the Coyle and Welch variables, 14 US variables, right, then we have to remove the DE and TMS, time spread, right? We have to remove these two variables because these two variables are a linear combination of other variables within that X set, right? So basically, we have DE here, DE, so dividend payout ratio. So basically, this is the linear combination of DP and EP, right? And we have here term spread, TMS, which is the linear combination of the long-term yield and short-term yield, okay? So there exists multicollinearity. So these are collinear predictors, right? So in order to address the multicollinearity, we have to remove these two variables from our data, okay? So here we are again defining our XM2 role, right? Okay, and let's start with expanding. So we are defining XM2 expand, right? And excluding the number 6 because it is in the number 6 column and it is in the number 13 column TMS, and that's why we are excluding 6 and 13. So one thing, if you are not using Coyle and Welch data, but if you are using some other variables and there exists multicollinearity, the linear combination of the other variables within the X data set, then you need to remove those variables from your X set, right? Okay. If there is no multicollinearity between your variables, then you have to comment out these codes, how to comment out these codes like this. So it's not gonna run these codes, okay? There's just notes there, okay? So, but we need to remove these two. So I'm going to run this one. Now we have XM2 expand. Next thing we have to do is that we have to standardize that XM2 expand. Standardization means that we have to subtract the mean and divide the standard deviation so that we can have the mean 0 variant as standard deviation 1, right? So we can save that as X tilde M2. Okay, so X tilde M2, after X tilde M2, we save that, we're gonna run the PCA. So here, PCA means principal component analysis. Okay, let me just summarize. First, loading the data, defining variables, right? And then we had the forecast routine. First, with the predictive mean, right? We calculated. Second, with the predictive regression, which is based on estimating ARDL 01 model. And we have done the ARDL 01 model with rolling window, with expanding window, and with the combination of those windows, okay? Now, third is the diffusion index, right? So in the diffusion index, what we do is that we run the PCA analysis, right? Based on all the predictors we have, we generate, let's say we are generating one factor, right? Which is explaining most of the variations in all the predictors, right? So here we are creating the eigenvector here. Let me get through my notes. I want to make sure I'm in the right direction. Yes, we are computing eigenvectors, right? And then here X tilde M2 is this part, right? That's standardized one. And this is x tilde m2, right? Now, what would be the dimension of this? Previously, when we were not excluding DE and TMS, we had the 16 by 16 dimension. But if we are excluding DE and TMS, then here observations, here dimension would be 14 by 14, right? And what is meant by one here, meaning that we are only generating one factor, okay? So change the last input to change the number of PCA. For example, if you want to do 2, you can do the 2, okay? And then we will get the G hat M2 here, and then we multiply this with the X tilde M2, we will finally get our factor, our one factor, right? And we are going to use this factor, right, as a predictor and for the excess market returns for the UK. Right, so we are going to estimate ARDL, right? So our dependent variable, our predictor, the factor that we just got from the PCA, 1 mean forecast horizon is equal to 1 month, 0 no lagged variables of dependent variables, and 1 for the other variables, right? And then we're gonna save all the results in forecast DI based on the expansion, right? So this is based on the expansion, okay? Now, we have to repeat everything all again, removing DE and T to the two variables in 6 and 13, right? Column 6 and column 13, right? And then repeat the PCA and estimate ARDL and save the results. And then we have to save the forecast DI combined, right? Combining both rolling and expansion window. Okay, so then we have forecast combine based on the so calculate the mean of the forecast expand PR and forecast roll PR and then forecast window combine, right? And finally, we're going to display these results. Okay. So let's just run this section. I hope, yeah, I did that, yes, before. Yeah. So now let's run this section. Okay, so here we have, I mean, just in the command window, you can see the results for M2 forecast based on prevailing mean, forecast based on combination, and forecast based on diffusion index combination, right? Now, we have to compute the actual values over the out of sample period. So we are going to calculate this and save as actual, right? Let's run this section. And then we have to compute the mean squared forecast errors. Okay, so first of all, we have to define what is the forecast error. That is the difference between the actual value minus the forecasted value based on prevailing mean, right? And then we have to calculate the mean squared forecast error based on the prevailing mean, meaning that we're gonna first, the forecast error is this, we're gonna scare it, right? And after scaring it, we're going to take the mean of it. So that's how we call it mean squared forecast error, right? Based on the prevailing mean. So this is for the benchmark model. Similarly, we will do this for the predictive regression with the expansion, predictive regression with the rolling, and then combining both predictive regression and, combining both expanding and rolling. And then combining the expanding, rolling, and the window combine of both expanding and rolling, right? And calculating the mean squared forecast error of that. Then we have diffusion index with expansion window, diffusion index with rolling window, and combination of rolling and expansion window based on diffusion index, right? And finally, we're going to calculate the mean squared forecast error ratio, okay? So expand PR divided by mean squared forecast error by based on the PM. And then we will compute the R square, out of sample R square using this formula, right? So what it says here that 100 times into 1 minus mean squared forecast error of the PR based on expansion divided by the mean squared forecast error of the based on prevailing mean. Okay, So once we are, okay, now let's run this section. Okay, and it's done. Second, we have to compute the Clark and West statistics, okay? So based on the Clark and West statistics, what we do is that, let me get through the notes. Okay, so basically in Clark and West test, we use the F value from each predictor, right, as a random variable, and then we're gonna test this against the intercept, right? And that is basically our Clark and West test, right? So here we have d hat expand predictive regression, right? So mu hat PM raised to power 2, 1 is the 1 month horizon, and j the number of predictors minus u hat expand PR raised to power 2. So element by element, right? And then we will calculate the F value, right? So F value is, once we calculate the F value for the expanding, so we're going to repeat the same for the rolling, for the window combine and combine, diffusion index expands, diffusion index rolling, everything same, just repetition, okay? And then finally, we're going to save the Clark West values here in the in this 54 by 1. 54 by 1, yes, it should be 54 by 1 vector, right? No, wait a minute. Is it 54 by 1? Oh, okay, I will, once we run, I will check that again. And then we have for each predictor, for loop for each predictor, right? And we're gonna run the OLS for this. So basically F is F hat as a dependent variable, and so only using intercept. So here we're gonna only using intercept, yes. So F hat is independent variable. We have here intercept, and we're gonna run the OLS, right? And we will get the save our results for each predictor in CWJ, right? So and by the end of this, we will have this CW, and that would be definitely 54 by 1. Yeah. Yes. And then next is K, 1 to size forecast combined 2. So in this case, we have, yeah, we're gonna run for K equal to 1 to size, right? And then again, save those results in CW again, right? And then finally, we're gonna have the run again all the OLSPs for the F as a dependent variable, and then using the intercept as against the intercept, and then save the results in CW, Clark and West statistics, and then finally, we're gonna display the table. Okay, so let's just run the compute Clark and West statistics. Okay, so here we have the results. Okay, so we have the MSFE ratio, we have the Clark West test statistics, and we have the R square out of sample. So how are we going to interpret these results? First of all, based on the Clark and West statistics. So in this case, how we define is that, how we interpret is that, so positive, if there are positive and large values, that means that they have improved, the predictor has actually improved the forecasting. But if there are negative values, meaning that they're most likely adding noise, right? So here, what we have the Clark and West. So mostly we have the 1.17, 1.5, right? 1.08, 1.4. No, this is negative. 1.2, 1.1, 1.7. So basically, I think 1.7 is the highest 1.17. So 1.7 is the highest one, right? So meaning that DI, diffusion index width based on the expansion, right? So this is basically improving the forecasting model, right? So we are testing this against the alternative, which means that prevailing mean is the good forecasting model, right? So what we do in here is that this is 1.7, right? But our critical value of 1% is 2.33, right? And if we are using the significance level 1%, then it means that none of them is higher than 2.33, right? None of them is higher than 2.33, right? So meaning that we are rejecting, we are not rejecting the H naught, right? So because we do not find any of these predictors significant at 1%, right? Which is the 2.33 value. Okay, so we are not rejecting H naught here. Okay, and then we have MSFE ratio. MSFE ratio is basically how we interpret that. If MSFE ratio is less than 1, that means that a forecast combination is better than the forecast based on the benchmark model, which is prevailing mean, right? And then in this case, if it is less than 1, then it is better. So we have 0.9919, 0.9998, 9998. Well, we have few predictors, 98 and 99, but I think they are, well, based on this, we can say that these are really better combination than the forecast based on prevailing mean. At least they are less than 1, even though 99 or 998, maybe this one is better. 98, 9, everything else is 99. Yeah. Okay. And then we have the R-square, out of sample R-square. So how we interpret the out of sample R-square. So if it is negative R-square, then that means that model is worse than the benchmark model. But if it is positive, then that means that model is basically improving the forecasting accuracy. So positive R-square, this is positive R-square, but it is not that, bigger one. It's just 0.21, right? This is okay. This one is 1.64, right? And then we have, well, most of these are negative. Yeah. Okay, this 1.303. So, okay. So here, this is less than this. This is basically positive and bigger compared to all the predictors. And we also found that this has the critical value, well, it is less than 1%. Sorry, 2.33. Anyway, so for DIY here and for here, we can say that at least this one is improving the forecast accuracy, right? Okay, so that was the let's run. Yeah, I already did that. Let me just check the K here. Yes, it is 3. That's right. Cast. Yes, that's right. Right. Okay, because we have the rolling predictive regression based on rolling predictive regression based on expanding window and predictive regression based on window combination. So all of 3 are together in forecast combine, right? So that is for that. So K is 3. That's correct. Okay, and yeah, I want to make sure CW, this one dimension is 54 by 1. CW. Oh, Yes, it is 54/1. Okay, that's correct. Okay, so that was the out of sample analysis, and we done that. Okay, and then based on Clark and West test and R square out of sample and MSFE ratio, we try to find out which model is the better, improving the forecasting, right? Okay, so let's go to data mining check. Okay, so okay, I'm gonna close this, and I'm gonna run this. Okay, now start with the data mining check here. I'm gonna click this and open this. Okay, so again here we have to load data starting from December 1993 to 2019-12. Okay, and we have obviously 313 observations. With when dropping out, then we have 312 observations. Again, defining the variables, everything is same. We have test stock, we have dividend yield, right? And we have the risk RF, the UK T-bill rate. So this is not basically total return index. Okay. Then we will compute the UK variables, right? As before, we calculated this excess market return with 312 observations. We calculated the term spread and the dividend yield, right? Okay, let me just run this section. Run and run. Okay, and then again the same, we are going to load the Goel and Welch data, the 14 US predictors, and basically they are from 1973, but we need the data from 1994 to 2019. So right, so we're gonna load that data and this. Now again, compute market excess return. So everything here is same. Defining the variables. Okay, what is the total number of observations, right? And what is M1? What is M2? So, and then we define the set of variables as X, the set of predictors as X. And here our forecast horizon H is equal to 1. And then finally, our number of predictors is 16, right? But later we will delete 2 of them, right? And then for saving the results, we have created these vectors and matrices. Again, iteration over the out of sample period for 1 to 156 observations. Then we have for loop within a for loop for the number of predictors, which is J is equal to 16. And we will do the forecasting based on prevailing mean. We will do the forecasting based on predictive regression and using the expanding window, using the rolling window, and using window combinations, right? And then here, now we are doing the PCA because these are going to be a problem with the PCA and kitchen sink regression. So that's why we are removing the DE and TMS in the PCA and kitchen sink regressions because of the multicollinearity as explained before. So again, defining this as deleting the TE and TMS, but then it's going to be 14/1, right? No, sorry, 156/14, yeah. And then we will have X tilde, which is the standardization of this X to expand, right? Mean 0, standard deviation equal to 1. Then we will run the PCA analysis. Here we have 1 factor. We are doing 1 factor. If you want to do 2, you can do the 2. And then we'll get the factor F hat M2, and finally get the estimate ARDL and save the results in gamma hat M2. Okay, and then we're gonna get, sorry, these are the coefficients, and then we're gonna save the results here in forecast DI expand M2. Okay, so same for rolling, and then finally we do the diffusion index combine. Okay, so so taking the mean of the forecast expand PR, rolling PR, forecast window combine, and display the results. So let's just do the same in this section. Right, so we have we have results here. Okay. Now we have to compare the mean square forecast error. For that, we need the actual values. So calculating the actual values over the out of sample period, and then computing the mean square forecast error. Okay, now here the difference is coming right. So this is already done. Calculating the U hat, right, meaning the forecast error, and then mean squared forecast error, calculation of the mean squared forecast error, right? And similarly for all other set of forecasts. So then in the end, we're going to have MSFE ratio, right? And then we have the MSCF expand PR. Now we have to create this F value, right? So let me just check my notes. Yes, now we will compute for each case the F value, right? Means squared forecast error F value. And once we calculate for each case, then we will do the bootstrapping, and finally we will get we will get the final table before that, before bootstrapping, sorry. So yeah, once we get this F value, we're going to make a table of this, okay? And let's just run this section. Okay, so what is the maximum value MSCF here? Okay, so the maximum value is 2.61344, right? So that is basically the maximum value from the results we get. Next is that we have to compute the distribution of the mean squared forecast error F value using the bootstrap. So first of all, we're going to run the kitchen sink regressions here, right? So we have X2 as the predictor variables, right? And we have the results KS. So basically, this is the running kitchen sink regressions, right? And then we're going to get the residuals from this and save that as epsilon hat KS, right? Okay. And after this, we get the residuals from OLS, right? We're going to save this in this epsilon hat KS, and then we will do the bootstrapping, right? So meaning that we will simulate for 100 times, right? So, and then we will save those results in max MSEF bootstrap, okay? And here RNG default mean, we are using the default simulator here. So for loop starting from b equal to 1 to b, meaning 1, 2 until 100, right? So 100 times simulations. So for that, first of all, we are going to generate the error term, right? So this is basically the simulated error, okay? So, then we will generate, once we get the simulated error, then we will generate a new y. So what is this? Here is, this is the y1 is the same as the historical data, right? And we have the mean of y, then we have the epsilon hat ks, right? Which are the residuals here, right? And this dot is element by element multiplications, and then we have the generated error u underscore b, right? And these are the vectors and matrices for saving the results, right? And everything else is now same from M2, 1 to M2, iterating over the outer sample periods for 1 to 156 observations, for 1 to until 16 predictors, right? For all the 8 set of forecast. Prevailing mean, predictive regressions, expanding, rolling, combining, window combine, and then we have the PCA, right? And based on only one factor, right? And this is also based on expanding, rolling, and combine, okay? And finally, we will have the we will calculate the mean of the expanding PR, forecast roll PR, and forecast mean combined, right? And let's run this section. Did I run this section? Yes, we got the p-value. So that was the p-value, oh God. And now this is bootstrapping until this point, yeah? I did something wrong. Oh, epsilon t had identified that. Okay, I didn't run this section, right? So first run this section and then run this. Okay, so this is taking some time. So basically this is like this, taking some time. So until then, I want to summarize what we have done so far. So basically what we are doing is that in data mining codes, we are just, we have computed the MSE F value, right? And we have found the maximum value that we get from the history, right? And then we have done the bootstrapping, okay? Basically we're computing the distribution of the MSEF, right, using bootstrap. And for that we are using kitchen sink regressions and kitchen sink regressions. Yes, and PCA, but before that, make sure that you are removing the two variables, the USDE and TMS, right, from your regressions, because these two are causing multicollinearity. Okay. So that was so here we removed these variables, right? And again, here we remove these variables. Okay. Okay. So finally, our bootstrap p-value is 0.3000, right? So how we are going to interpret this value? So 0.300 p-value for the bootstrap, meaning that there's 30% probability that the improvement we have observed in the real data could occur purely by chance, right? Under the null of no predictability. That's what it meant, right? So I was just taking a look that we have commented out these one, right? So what we are doing is only running the PCA, yeah? And then estimating the ARDL, right? Based on the predictive regressions, okay? Right, so now we will calculate the mean squared forecast error, and we will have the actual values, right? So in order to calculate the mean forecast error, so error actual minus the predicted one, and then mean square forecast error for every for every forecast, right? And B for bootstrapping, right? Because we are using bootstrapping sample here now, okay? And once we do this, Let's just run this. Okay, and then finally run this. So basically, p-value is equal to mean max of MSCF bootstrap higher than the max of MSCF. So we have calculated the maximum value of the MSCF based on the historical data, and based on we have also calculated the max MSCF based on the bootstrap. And this is basically telling you that how many times the max MSCF bootstrap is higher than the max MSCF from the historical data, right? So this is basically telling you that, right? Yeah, I think we are done with the data mining here. Okay, so that was data mining. Next is we are gonna check the economic significance of our return forecasting, and we do this by using the certainty equivalent return gains. So I'm gonna open these codes for certainty equivalent return gains, right? So everything else same, loading data, right? And defining the UK variables and then computing the UK variables. So I'm gonna run this section one by one here, or maybe I will do it in the end. And then, yeah, I will do it in the end. Okay. So defining the UK variables, and then defining the Goel and Welch variables, right? And then we have computing the return forecast and portfolio weights. Now we have to compute here portfolio weights, right? So basically we have each set of forecast, and we have to calculate the forecast in portfolio choice, which basically need to forecast the variance, right? And so we have to calculate this forecast VOL, right? And for this, we use a very simple model, which is moving average volatility, right? So everything else is same. So T, M1, M2, defining the set of predictor, right? J16 and columns and vectors and matrices for serving the results. And now here we are also have to calculate the forecast VOL, right? Okay, and then we have to calculate the weights and save those here in these. Okay, based on 8 set of forecasts. So 1, 2, 3, 4, 5, 6, 7, 8, right? And then we have to calculate the portfolio return again for the 8 set of forecasts and save these. Save these in these columns and matrices. Now, what is M size equal to 60 here? Basically, before that, I wanna discuss these. So what is this is WPM. Basically, WPM is the weight to the market index based on prevailing mean. So based on predictive regression, expanding, rolling, window, combine, and based on the Pagan index, expanding, rolling, and combine, right? And so then we have the portfolio return based on the prevailing mean, and again, the expansion, enrolling, predictive regressions, and the Pagan index, right? And then we have MA size equal to 60. right? So MA size equal to 60 basically means that 60 is for volatility. So MA is moving average and 60 is for volatility. For example, if we are forecasting the next month variance, then we will use the last 60 months to forecast the next month variance, right? To compute the variance. And each time we will update the new data point and recompute for the 60 months variance, right? And then finally, we will use that as a forecasting variance for the following period. And then we have relative risk aversion, which is equal to, we set equal to 5. And we were going to define the upper bound, weight upper bound, and weight lower bound. So upper bound is 2 and lower bound is minus 0.5. But we can also, this is commented out because it's just an example given to you that we can also use the relative risk aversion equal to 3, and with lower bound you can change this to 1 as well. And now here we have upper bound 1.5 compared to 2. But this, I'm not going to run this, but I'm going to basically run this, okay? So again, iteration over the out of sample period, M2, 1 to M2, and then, so we are defining the Rx M2 expand, right? And we are also defining the XM to expand our predictor variables. And then based on the rolling, we also define our dependent and independent variable, right? And here we are generating forecast volatility, right? So basically the standard deviation of previous 60 months monthly returns, right? So now here we have used if else, okay? So meaning that if initial sample period is less than 60, right, then we will use the equation. We will use the else equation, right? Okay, but if the sample period is, it's bigger than 60, then we will use the standard deviation form, last 60 months return. So this is what it means, okay? And then we have the, we're going to save the results forecast PM M2 here, right? And next is our weight of the based on prevailing mean. So weight based on prevailing mean we have to calculate is equal to 1 over relative risk aversion into forecast PM M2 divided by the forecast volatility M2, forecast volatility M2 raised to power 2, right? So this is going to be the variance, okay? Right, so if weight based on prevailing mean is higher than the upper bound, then we will write this as with the upper bound as a weight, right? So once we compute the weight based on prevailing mean, then we have that if it is greater than upper bound, then we will write it as the upper bound with this weight. And if it is less than the lower bound, then we will write it as with lower bound as a weight, right? And this is basically explaining that once we have weights, we can calculate the portfolio returns from it, right? So this is basically the excess return. This one is the excess return. We have the risk-free rate, right, RF, and for each predictor, we have for loop, okay? And then we will compute the forecasted market excess return using the estimate ARDL, right? Once we do that, based on that forecast market excess return, we will then compute weights based on each predictor here, right? So again, we compute the weights based on each predictor J. And again, if it is higher than upper bound, then we're gonna write with upper bound as a weight, and otherwise write with upper bound, write with the lower bound as a weight, right? Okay, so one thing I want to mention here that we are using the same volatility forecasting. So in any computation of weights, we are using the same volatility forecasting, right? Just want to make sure that, yes, everything is right, correct. Okay. And finally, we will compute the return based on the portfolio, based on the predictive regression, right? So here we have the excess return, this one, excess return, right? And we have the risk-free rate, okay? And we're gonna estimate the ARDL for rolling, right? The same as for expanding. And we're going to repeat this for every set of forecast. And once we finish this, we will have once we finish this, we were going to display the results, the WPM of M2, W combine M2, and WDI combine M2, right? And okay, let's just run this codes up to now here. Okay, run this, run this, run this. And this is the entire section up till this point. Okay, right. So this is the display. This is the table we got here. This one, right? Okay, and then we have now we will compute the annualized certainty equivalent return gains, right? So important here is that annualized, so meaning that we are multiplying it with 12 and also with 100 to get the percentage form. Right. So sorry, I just changed it. So this is 1200. 12 mean annualized and 100 means percentage form, right? And we have the variance of the portfolio return here based on the basically prevailing mean. We have the relative risk aversion here, okay? And then we will calculate the CER gain, PR expand, which is equal to the CER PR expand, certainty equivalent return for the predictive regression with expansion window minus the CER for the prevailing mean, right? So that is going to give us the CER gain for predictive regression with expansion window, right? So we are going to repeat this for the rolling window, combine, diffusion index expand, diffusion index rolling, combine, and then finally we'll display the table. Let's just run this section. Okay, so we will have this table now, and let's see. So the negative values basically indicates that the utility is you're losing, right? Yeah, so your utility is worse than the utility from using the PM forecast, while the positive values indicate the gain, and which indicates that utility is higher than the utility from the prevailing mean. So we have this positive, right? It's not that big. Okay, this one is 1.5 bigger. This is 1.4. Okay, we have 1.6 here as well, 1.7. Okay, so 1.6, right? So in summary, the negative values are indicating that your utility is worse than the benchmark model, while positive values are indicating gain, that is utility higher than the benchmark prevailing mean model. Okay, so this is the interpretations. Okay, right. One thing I want to mention is that basically you have to how to you know added these codes based on your own country specific data. So that would be difference here, right? So basically we have UK variables here, right? Based on your own country, you're going to upload the data, you're going to have the CSV separated values file, you're going to have your own country return index, dividend yield, and T-bill rate, right? And then you will create those variables. And this one, if you're using the Goel and Welch, so make sure that for kitchen sink regression and PCA, you are removing the two variables, right? And if you are using the other variables, and if you see there is a multicollinearity, you still have to remove those variables, okay? And so the change would be here in your data, right? And then the changes would be exactly here, how you're going to define your predictor variables, right? Well, this is set for R. You can try with a different numbers, and make sure that you are also removing this DE and TMS for multicollinearity, right? And yeah, okay. So that was for the certainty equivalent return gains. Okay, now we will run the in-sample regression, right? And for the in-sample regression, we're gonna click the program in-sample regression f.m, right? So here we have the data, right? The UK data, stock, dividend yield, RF. We have to compare the UK variables, right? And we have to display the summary statistics, including volatility, and including the Sharpe ratio, right? So how you calculate that? You will calculate that using this. And why we are multiplying this with 12? Because we want the annualized mean, we want the annualized standard deviation, we want the annualized Sharpe ratio, right? And then we're going to define the term spread and dividend yield, okay? And so the 312 by 1, right? Let's run these sections. Okay, so we got dy. Next is loading the Goel and Welch data, right? And then we have the predictor names. These are predictor names, the predictor variables, right? And we will calculate the mean. We will calculate the median. We will calculate the percentile 1 and the 99th percentile. And then we will calculate the standard deviation, right? For these predictors. Once we do that, next we will calculate the correlation, right? So basically, RHO row is indicating the matrix, and we will compute the correlation for each variable, right? So this is autocorrelation. And once we get the autocorrelation, we will save that in GW2 adjust, right? And another important thing here is that now in sample regression, it is important that we need to get the positive values for all the beta coefficients, right? And for that, if there are any negative beta values, we are going to multiply this with -1 to get the positive coefficient. So in your regression, in sample regression, if you see that there are some negative beta values, then make sure you are multiplying it with -1 to get the positive beta coefficients, right? So this is one important thing, okay? So in summary, we get the summary statistics, right? We have the autocorrelation, okay? And then we also have the beta coefficients, all beta coefficients positive, okay? Next, we have to do the principal component analysis for Goel and Welch predictors. So first of all, you have to do the standardization, right? So standardize them. And meaning that we have to standardize the three factors, right? Okay, and then we also going to remove DE and TMS, the variable in sixth column and the variable in 13th column. So if in your data there are variables, so you have to make sure that you are editing your codes based on the data set, in which data set you have, right? Meaning that if your variables are in column 8 and if your variable is another variable is in column 11, then you have to mention 8 and 11 here to remove those variables, okay? And then run the PCA and standardize the factors, okay? And then finally, we're gonna calculate the predictor correlation matrix, right? So once we get this correlation matrix, so basically this is for the presentation, meaning that you get a big matrix and it will be a repetitive correlations. So in order to make it a more clean table, we use we create it as a predictor correlation upper. So, and then we also create the, basically we set the lower triangle to NN, right? So basically we are excluding the diagonals to make it a more clean table, okay? Finally, we compute the cumulative returns. Okay, so so far we have done the summary statistics, we have computed the PCA, we have done the predictor correlation, and now we have to compute the cumulative returns, right? So here, H is equal to 1, meaning that our forecast horizon is equal to 1. So so since we are using 1, so there's no need for this, basically for loop. But if you're using like 2 or 3, then you need to have this, okay? And basically this is just a y variable. So we are going to save the results in RH here in this. And we have the J number of predictors, right? And we have to compute the in-sample results. So here we have the beta hat, right? And again, we are using here h equal to 1, so we don't need the, the for loop, right? And then we will run the bivariate regression models based on Coyle and Welch predictors, okay? So we have here in X variable, our first column is ones, and then from second column to last, we have the for each I, right? And here we have 100 times into market excess return, right? And we are going to run this 100 into market excess return on X variables, right? And then finally, we will use this and West here. We are going to use this estimator, newly West estimator. We calculate this newly West estimator, okay? And basically, this is basically almost same as OLS. We just want to correct the standard error. That's why we are using N West here. And once we run this, we're gonna get the beta hat here. We're gonna save the results for all predictors here, okay? And then we will run the multiple regression model based on principal component analysis, right? So we have again there N West, right? And we will save all the results. So basically, we have here J is 16 predictors, right? And yeah, so 100 into RH we were going to run this against the X, right? The PCA factors, right? And then we're going to have the three coefficients from the PCA factor, right? Coefficient T stats for first, second, and third PCA factor, right? So we're going to have these results. And finally, we will compute the fixed regressor wild bootstrap p-values, right? And for this, we need this, the kitchen sink regressions, okay? And make sure you are removing the variables which are causing the multicollinearity, okay? And once you've done this, we were going to run the OLS and we will save the residuals in epsilon hat, okay? And then we were going to do the bootstrapping. We were going to do the simulation 100 times, okay? And 100 times simulations, and we're going to save the results in this matrix, okay? And finally, RNG default means that we are using the default options for our simulations, okay? So everything is same here from within this for loop when we're starting the bootstrapping. So basically everything is exactly same as above, and we're just using the bootstrap sample and rerunning all the regressions for basically each predictor and running the PCA factors. And then we are going to save all the t-stat for each case, right? Once we get all this, then we're gonna save t-stat all of these here. Right? And then we have the next is for j equal to 1 to length, right? So in this case, basically for this one, after we are save all the t-stat values here, next is that for this each predictor, right? We will count that how many times the t-statistic is basically higher than the t-statistic we get from the historical data, right? So basically, this is how we will compute the p-value. And then we will display the p-value in the command window. And then after that, we were going to save all the results, okay? Right. So I'm going to run this entire again. Oh no. Error. Okay, let me run this one by one. Okay, so up till this point, right, so these are basically the results based on all the predictors, individual predictors, and based on PCA. So actually, I have saved the results. I'm going to show you the saved results here. So can you see my MATLAB screen, or can you see my Excel file? Hello? Meaning that you can see the Excel file? Okay, you cannot see the Excel file, right? Let me stop sharing, and then I want to share the Excel file now. This one. Okay, now can you see the Excel file? Okay, great. Now we have the summary statistics from the in-sample regression, right? And these two for the term spread and the dividend yield are UK variables, while these are the predictors from the go and wedge 14 US variables, right? And we can see that here mean, well, this is the highest one I highlighted with negative, and standard deviation, the highest one is for the log EP and log DE, and this indicates the autocorrelation. And right, so this is actually what we meant by when we clean the table using the codes in the MATLAB. Okay, so basically we are removing this part here so that we can clearly um, um, see the results and interpret the results. Now, here we have very high correlation between log dy and dy, and we have a high correlation between log dy and dp. And again, we have a very high correlation here with the long-term yield and the T-bill rate. So this is T-bill, T-year bill, right? And this is the long-term yield, okay? So we have the highest correlation here. Otherwise, other yellows are also indicating the high correlations, right? And then finally, we have the in-sample results. So basically, these are the term in TY. So we have the 2, 7, and 5, 1 coefficient, right? And with the R square of 0.51, 1.84, right? And our boot p-value is 0.124 for these, right? And finally, we have our principal component factors 1, 2, 3, right? And I think that the first one is the one which is explaining most of the variation, so it is the highest 0.41, right? Okay, and yeah, I think that's it. And if you have any questions, please let me know. Okay, so thank you.